Okay, let's have a look. We're going to look at something a little bit different today. We're going to look at another kind of force. This is going to be called a restoring force. If we ever change in shape due to an application of force, it's called a deformation. Okay, so when we start to study the stuff that we're going to study now, I mean, it's going to have some application to things like trebuchets, but this is kind of engineering specific stuff. Like if you were going to be building bridges, for example, this is some of the stuff you'd have to start taking into account. It's sensitive to the materials that you use lots of times. So for small deformations, so if we're going to slightly, and what we're going to talk about today are stretches and compressions. Okay. For small deformations, two things are true. The deformation is elastic. What does that mean? What's it mean if something is elastic, just based on physics?
It'll go back to however it was.
Yeah, it returns to its original shape. Think about things that are elastic. You know, they're made of elastic. They stretch, but they pop right back, right? So there's one thing that's true. The other thing that's true for small deformations is that the restoring force is proportional to the displacement. That's called Hooke's law. Okay, so the amount of force, you can think of it two ways. The amount of force required to compress something by a certain distance, call it delta L, to change the length. So delta L is the change in length. Or you can think of the amount of restoring force provided by the object is going to be proportional to how much it's been deformed, how much it's been stretched or compressed. Yes?
What would be considered a small deformation?
Okay, so yeah, and we say this kind of stuff a lot in physics. What does small mean? Small means, I'll give you more details later, but small means that relative to the, in this case, the length of the object, it's going to be fairly small percentage of the length, okay? It's going to be dependent on the material. So objects that are highly elastic, the deformations can be bigger for objects that are highly elastic than they could for objects that aren't as elastic. Yes?
What was delta L again?
Delta L is change in length. So all this is saying is that force is equal to some constant times the change in length. Okay? We can demonstrate this pretty easily. If, where did I put my weights? I just have them here. Oh, here they are. Okay, so if we take, like, I've got a spring up here. Springs are made of metal. Metal is highly elastic. Springs are good things to use because although they're compact, the length of the piece of wound metal is pretty long, actually, right? So if I put on this spring, if I put a 500-gram mass, and I look at where this ends up ending up. It ends up at about 13 centimeters if I look straight on. It's been, so the length changed by 13 centimeters from its neutral spot, which we'll call 0 right there. Okay, that's 0. Okay? What do you think is going to happen if I double the weight? So I've got 4.9 newtons on there now, and add another 4.9 newtons. What do you think is going to happen to the
26?
Yeah, it should be double. And it works out to be about 26.42. I mean, you know, close enough. My ability to read it. It about doubles it. However, if we keep doing this, we're going to get to a point where this doesn't work anymore. Right? If I put another kilogram on there, does it go down to 52? No, it doesn't. It goes down to about 55 or 56. So it starts to be nonlinear after a point, right? Only that was too big a deformation. It wasn't small anymore. So it didn't obey Hooke's law.
So it wasn't elastic.
Say it again.
So it wasn't elastic.
The question of whether it's elastic means if I let this thing go, does it return back? And it does. So it still was elastic. When I remove the force, the deformation is not permanent. right? It returns to its original shape. That's what it means to be elastic.
So it would be a small deformation.
But it's right, but it's not a small, it's not a small enough deformation for Hooke's law to hold, okay? And I'll show you a graph here that's really cool that kind of explains that in a second. A lot of times we use Hooke's law to describe springs. Springs, you know, we use springs all the time, and when we use Hooke's law to describe a spring, a lot of times we'll call this constant right there the spring constant. And what would the units of the spring constant be? What do you think? If I wanted to,
Kilograms per second.
it would, say it again?
Kilograms per second.
Not quite. Close.
Kilograms per meter.
Okay, so all we have to do, if we solve for k
Kilograms
here,
per second squared.
kilograms per second squared. Like, look what happens. If we solve for k, would you agree that? Oops, let's get rid of that thing. Would you agree that k just equals f over delta L? So if we want to know the units of k, all you got to do is figure out what are the units of f divided by the units of delta L. And that's going to be what? Newtons over meters. And what's a newton?
A kilogram meter per second squared.
Right, because F equals ma, right? So we just remember that. Units of mass times units of acceleration. So a kilogram times meter per second squared divided by a meter just gives us a kilogram per second squared. So is that important? No, not important at all. That's just what the units have to be, right? If we were to measure the spring constant K for some spring, the units would end up being units of kilograms per second squared. It's not supposed to be especially meaningful that those are the units, it's just what they are, it's what they have to be. Right? Okay, so Hooke's law is fairly simple, right? We can get more specific than that. This is for specifically for springs, because springs are relatively simple. And when you want to specify, let's go back to cars again. We always go back to cars with this stuff. If you want to specify the stiffness of a spring, what do you think you're doing? What are you really specifying?
Elasticity.
The springs are definitely going to be elastic, right? I mean, car springs don't flex very much, so they're definitely elastic. But if you're specifying, like, if you put the spring from a Hummer on a Ford Fiesta, that's not going to be a very smooth ride. How come?
The spring takes more weight.
Yeah, it takes more weight to compress. In other words, we'd say it's a stiffer spring, right? For a given amount of force, it's not going to compress as much as a spring that's a lighter weight spring, right? Does that make sense? So you got to carefully match in a car. When you build a car or you replace parts on a car, you can't just put any spring on the car. You got to put a spring that's matched to the mass of the car, right? And how much you want it to travel. If you're driving a European sports car, do you really want that spring to have lots of travel? No. I mean, if you've ever been in like a Ferrari before, you can feel you feel everything. It's comfortable, but it's not comfortable in the sense that like a 1972 block-long Cadillac is, where you drive over any pothole and you wouldn't even know you did it. I mean, it's, right, the springs are so soft. But on a Ferrari, you want the tires to always be in contact with the road, and so the springs are going to be stiff. You're going to push those tires down, so as soon as there's a gap in the road, the tire's down. It's in contact with the road, right? So it's going to be a much stiffer ride in a sports car than it would be in a luxury car, let's say. Okay, so what if you wanted to, like, I'm not saying you want to do this, but let's just say for whatever reason you wanted to lower your car a little bit. What are your options? If you want to lower, and that would be crazy to do, but let's say you did. Well, if you just cut the spring, right, to lower the car, which you could do, right, do you think that's necessarily going to have no impact on the ride? It's going to have an impact. What kind of impact do you think it would have? Well, we got to go a little further with this to explore what are the ingredients that determine what this constant is going to be that relates the force required to compress something by a certain amount. Okay, so we got to go a little further than just this elementary equation. We got to go to the next level. Okay. Oh, one thing I did want to mention to you though. Okay, so you asked some good questions about what does small mean, right? So here's a good diagram that for the most part, I mean, every material is going to be slightly different, but this is very representative of solids for compression and tension when you're stretching or compressing. So there's going to be this region in here where if you're looking at force is on the horizontal axis and displacement is on the vertical axis. So read this as how much force is required to displace the spring by a certain amount. Okay, notice that when it's really small, right, when the amount of displacement is really small, what do you notice about the shape of that curve?
Linear.
It's linear, right? Well, that is, I mean, if you look at the equation of that line, I mean, they've got this one kind of backwards. It's delta L equals some constant times F, right? But we could just as easily divide both sides by K. Let's call this one K1, right? And if we divide both sides by K1, couldn't we just get the equation F equals 1 over K1, which we'll just call K, times delta L? My point being that these are linearly related, and the line goes through the origin, right? So this fits perfectly what we were just talking about, right? That's a region where Hooke's law is obeyed, right? There's a linear relationship between force and compression or stretch of the object, spring, let's say, right? Okay, if you go down a little further though, you can still be within that elastic region like we were up here when I overloaded the spring. So it's still, when I remove the weight, is going to spring back to its normal position, but above a certain point, it ceases to be linear. And we kind of saw that just a little bit over here, right? Now it starts to be nonlinear and it's harder to predict. So it's much easier for us to model the restoring force for a deformation when we're in this linear region. That's where we try to stay. And if you keep going with that, you can go too far. You can go so far that the string gets stretched to a point where it's no longer elastic. It's permanently deformed. And you've probably seen springs, when they get oversprung, what happens to them? I mean, yeah, they just kind of, the coils don't come back together, right? If you walk over in the lab and get an example right now of some that have been ruined that way. So you get this permanent deformation, and then if you go too far, at some point, it just fractures, right? And then it breaks and there's no longer any force because it's broken. Yeah.
That elastic region after the Hooke's law, why does that level out? Wouldn't it be getting higher at an increasing rate?
Okay, so what happens is, at some point, like imagine this spring. At some point, this spring has been pulled apart to the point where the coils won't come apart anymore without actually rupturing the material, right? And the spring is a model, even though the spring's easy to see. If you think about the coils of the spring as being kind of the molecules in a substance, that's sort of the way it behaves in a substance also, just like a solid, like a steel rod, for example. Okay. And then at the very end, you can see it starts to do this. Is what I think you're talking about. At the very end, it starts to fail or get close to failing, and now all of a sudden, small increases of force are making the thing stretch out quite a bit. So it's like it's getting to the very breaking point, and then finally it snaps, right? Fractures.
So at the end of the elastic region, it'll kind of only go to a certain point, and it won't go any farther unless it breaks.
Right. And it's different for different materials. Like if you look, for example, at a human ligament, this is what a ligament looks, or a tendon, sorry, not a ligament, tendon. This is what a tendon looks like. Okay, and this is really important that it functions this way. It's been specifically, it's evolved to function in this way. Think about what this does. If you look at the displacement versus force curve, there's this region called the toe region down here where it doesn't change very much. You got to increase the force quite a bit initially to get a little bit of extension in the length of the tendon. And that's because you want to be able to apply, I mean, you're walking around, you want to be able to apply forces to the ground, right? But when you get into this region, when the forces are higher, relatively high. Notice that it becomes linear and it starts to be stretchier, right? But it's still elastic in that region. And so when you jump, like you talk about jumpers in track or in basketball or anything, do you really need to have super strong muscles to be a good jumper? You don't. I mean, it helps, but the main thing to being able to jump high is not how much force you can apply, it's how quickly you can load your tendons and your ligaments, the connective tissue. And if you're a person that has, if you're just predisposed, if you have the right connections, like people that typically can jump high typically have high calves, because that means that they can load that muscle quickly, and then there's a longer tendon to be more elastic. The longer it is, the more elastic it is, right? So you load that tendon up and it stretches and it pops back, and that's what shoots you up in the air, right? So it's really about being elastic, and as you get older, I can testify to this, the elasticity of your connective tissue just reduces dramatically, and you just can't jump as high anymore, right? So
Can you do
I promise you that's the way it works.
Can you like do stretches to increase your movement and tendon?
Well, you can, yeah, you can do stretches, but as important as that, you want to do like plyometric response stuff, where you're loading and unloading quickly, like jumping off the boxes, and you're doing things like that, where it affects the physiological properties of the connective tissue, but also it improves your ability to quickly load and unload the connective tissue.
Tissue's not change.
No, it doesn't change a ton, but it does a little bit. I mean, tissue does respond to use. Like I know that, like my dad, he had a hip replacement, and his surgeon said that probably the reason he was able to go so long without having to have this replacement done, he had this genetic kind of a malformed hip capsule, is that he ran so much. I mean, for many years he ran over 100 miles a week, and motion is lotion. That's it. The more you use the weight-bearing cartilage in your body, the better it responds to those forces, and it actually rebuilds itself. And so yeah, there is a physiological response to exercise that's often more profound than you think it would be. So plyometrics really work. You want to jump higher. Okay, moving on. So here's an example of how different materials are affected differently. If we take like 3 guitar strings, identical lengths to start with, and we load them up with the same weight, it's not surprising that some guitar strings are going to stretch more than others. What kind of a guitar string do you think is going to be easier to stretch? The thicker E string or the thinner, what is it, A string at the bottom?
Thicker E.
Yeah, it's going to stretch more or less?
More.
It stretches less. It's going to be harder to stretch the thicker string than it is the thin string. Okay, we'll see why in a second. Materials matter. If you've got a nylon string, that's going to stretch much more easily than a steel string would. Okay? So here's the equation that gets more specific than Hooke's law. This is like Hooke's law on steroids. This gives us all the, what's really contributing to that spring constant K that we talked about. So if we've got an object, and just for convenience, we'll just say, take a steel rod or something like that. So either we're going to stretch it, right? We're either going to stretch it by pulling it, providing tension along the rod, or we're going to compress it. And either way, the same equation holds, which is what's interesting. For most substances, but not for human bone. Human bone is more susceptible to compression than stretching, I believe. Can't remember. We'll see when we look at the chart. I think that's right. So here are the parameters that are involved, right? If we want to, we could rewrite this equation. These are kind of probably look a little strange right now. What's a capital Y? Well, we'll talk about it. What do you think A is?
Cross-sectional area.
Cross-sectional area. F we know. What do you think L naught is, or L sub 0?
Initial length.
Initial length. Yeah, there you go, initial length. So if we wanted to kind of turn this around a little bit, and let's solve this for F, just so we can compare it to Hooke's law as we wrote it. If I solve for F is going to be by itself on one side. On the other side, I'm going to have some constant times delta L, right? Well, what's the constant going to be? What do I have to do to get that F by itself? On the top, I'm going to end up with Y A divided by initial length, so that's my constant, right? Times delta L. So all this stuff is really what was responsible for that K in Hooke's law. Okay? So now, look at this. Look what's going to happen here. So the amount of force that is required to compress an object or stretch it by a certain amount, if I increase the cross-sectional area, what is that doing to the force? It's increasing the force, isn't it, right? It's going up because that's, the force is proportional to the area, isn't it, right? If I double the cross-sectional area, I'm doubling the amount of force required to move this thing delta L, right? What about the spring length? It's inversely proportional to the spring length. So what happens if you shorten the spring length? What's actually happening to the spring constant? It's getting bigger. Yeah, right? So let's go back to our example. If you want to lower your car by cutting the spring in half, what have you really done? Well, if you cut the spring in half, you've just multiplied the amount of force required to displace that thing by a factor of 2. Or another way of saying that is, the same amount of force is only going to displace it half as far. So what did you do to that spring? Did you make it stiffer or looser?
Stiffer.
Yeah, you made it stiffer. Your car's going to ride much more harshly if you shorten the spring, right? Okay. And then finally, what's this Y? It's called the modulus of elasticity, or more commonly, Y stands for Young's modulus. Okay, and that's a property of the materials. You'd have to just look at a list for that stuff. Like, for example, here's a list of Young's modulus for a bunch of different objects. Like aluminum, it's 70. It's really big for, where's steel? I just have to go down a little bit. Steel's really big, right? Steel. And these aren't the actual numbers. These are the numbers times 10 to the 9th newtons per square meter, right? So these are big numbers, but notice how much bigger steel is than like aluminum. 3 times bigger than aluminum. Is steel considered to be harder or softer than aluminum? Harder. Yeah, right. So steel's the biggest on the list. I'm sure there are other substances that are higher than steel, but steel's the highest by far on this list. If you look at like a human tendon, look what a tendon is. It's 1, right? Tendons stretch a lot compared to steel, right?
Can we manufacture things that function like tendons? Like, is there anything else that we can make that?
People sure try to. I mean, it's hard to, and you can to some degree. Like you look at people that run on blades, right? I mean, then they just tune the blade in such a way that it tries to mimic a tendon, you know, by shaping it. And there's some other things going on. The blade, it's not actually. What that actually is a shear force. We'll talk about that next, because it's actually bending it this way instead of stretching it. Yes? Spider silk, that's a spider thread. That's like literally from a spider web.
Yeah, but like,
What's the substance?
no, what's this?
Meaning, well, what does this mean right here?
No, is that, there's.
Yeah, yeah. Yeah, so it's relatively,
We watched a video on that in biology, and it could like stretch so long and take so much force.
yeah, yeah.
Is there anything that's 0, like totally elastic?
Air. That's totally, that doesn't have, takes no force to compress, yeah, like air. Yeah. Right. Question was asked about, can you engineer a tendon? And the answer is not very well. I mean, it's the body is produced what it does really well. I mean, over millions of years, it's just been selected. Tendons have been selected to be just right. Look at bone. So bone for compression. Yeah, see, bone it's harder to stretch a bone than it is to compress a bone. Right? It's more resistant. Y is bigger for tension than it is for compression. Yes?
Would it be possible so if you can't engineer synthetically like a ligament, if you were to in a lab, create a ligament, would it be possible to use it as ligament tissue?
You know, I have limited expertise on this, but what's the problem with trying to do that? Rejection.
But not like in a human, but like, would it be a way to use the tissue for something that's not
Like a robot?
not necessarily just as a material?
Yeah, I mean, and that's what material science does. And material science is really interesting. It's physics. And material scientists would do things like they would maybe try to come up with a bionic tendon, something that's going to take the place of a human tendon. And so they would study what exactly does a tendon do. I mean, in minute detail, they would study what its force versus elongation profile is going to be. And then they would try to come up with some way to engineer something that's going to do something like that. I mean, and here's an example of how people could start to approach that. Think about like a one-ton pickup. Think how a one-ton pickup works. In a one-ton pickup, and I drive one, so I can testify to this, they're not the most comfortable riding trucks in the world, but they're not horrible, right? Even though the suspension can handle lots of weight, there's a softer part of the spring that is active when you're just driving around with an empty truck, right? And then if you start to load it up, that softer part of the spring bottoms out against the stiffer part of the spring, which then gets compressed, right, and takes the load better. And so you can do things like that. You can try to engineer materials where under one phase of stretch, there's going to be one material acting, and under another phase, there's all kinds of things you can look at. It's a really interesting area to study, though. Yeah.
If air is zero, where does liquids get into?
Liquids would be zero also, because they're inelastic. Did you had your hand up earlier, Richard?
Yeah, I was going to piggyback off yours, which.
Oh. Okay, all right.
Do springs wear out?
Yeah. Yeah, they do eventually.
Quickly, if they never.
No, good springs last a long time, but
Even if
but
they
they
never
do-
leave their elasticity.
they do eventually wear out. Yeah, I mean, there is some, there's mechanical movement of the molecules, and they'll stress and little cracks will form, just like they will in like a plane. That's how, planes have to get decommissioned after a while, because when you start to look at planes even though they're made of metal, and it's high quality metal, eventually the little bit of bending that they do in the frame and the wings and stuff, eventually they start to form little micro cracks, and that's when they have to then they can't get used anymore, because they're at some point they're gonna fail. Yeah.
So it would be the elasticity of like hydraulic fluid or something like that?
None.
That's,
Zero, because it's a fluid. It's completely inelastic. So this could only be a solid. This could only apply to a solid.
So something like a piston, the best we can get to a tendon.
Say it again. A piston? I don't know. I don't know the answer to that. I'm not sure what the state of the art is in artificial tendons, but I would guess it's going to be. I would guess it's just going to be some material that's highly elastic. Rubber's probably pretty good. I would think. Rubber's really durable, and it's highly elastic. It's very hard to wear out. Okay, so when are we out of here?
in a
1 minute.
Go, go, go.
Okay, wait, you have the ingredients to do the assignment. So now, this assignment is kind of interesting. It's going to ask you things like, what did I do on this assignment? I can't remember. Things like if you wanted to tune a piano, right? If you want to tune a piano and you need to stretch a string a certain amount, how much force is going to be required based on the diameter of the string and what the material is in the
For the
string.
entire piano?
What about the cello?
Cello
Well, I gotta say,
probably has a very, very small, not very elastic, but slightly elastic. It breaks really easy.
but it jiggles. That's why you were thinking.